So in this video we will solve the sums of class 12th physics chapter 8 electrostatics. Let's look at the first sum. A dipole with its charge minus q and plus q located at a point minus b and plus b is present in an uniform electric field E. So if we make this as our x-axis, this as our y-axis and this as our z-axis, so our charges minus q and plus q are located at, if this is plus b and this is minus b, so at minus b minus q charge is located and at plus b plus q charge is located, which forms a dipole with dipole moment p from minus q to plus q. So this is our dipole moment p from minus q to plus q. Now the equipotential surface of these fields are planes parallel to the yz plane. That means suppose this is a uniform electric field, and if this is a plane perpendicular to this field, then all the points on this field are having equal potential. So similarly what they have said is that the equipotential surface of this field is having a plane which is parallel to yz plane. That means this is a y axis and this is a z axis. So if so all points on this plane, that is yz plane, are having equal potential due to our electric field. That means our electric field is in x axis. It can be in either plus x direction or minus x direction. So we can say that our electric field of magnitude E is having direction in x axis. So I cap. So our E bar vector will be plus minus E I cap. That is, it can be either in positive or negative x axis. Secondly, they have asked us to find the torque that the dipole would experience in this field. So we know that torque is given by P cross E, that is the dipole moment into electric field, and since P is in y direction and E is in x direction, they both are perpendicular, so we can say that theta is 90 degree. So this can be written as PE n cap. Since P is in y direction and E is in x direction, by the right hand thumb rule we can say that the resultant torque will be in z direction. So instead of n cap we can write it as k cap. Now the magnitude of dipole is given by P equal to 2b times q, that is the distance. Minus q was at minus b and plus q was at plus b, so total distance between minus q and plus q will be 2b into the magnitude of charge. So the torque can be written as 2bq into E k cap. But since E can be in either x or minus x direction, so plus or minus sign. I hope you understood this sum. Let's look at the next sum. Three charges minus q plus q and minus q are placed at equal distances on a straight line. If the potential energy of the three charges is 0, then what is the ratio of q to small q? So solution, they have given a system of three charges placed linearly, that is minus q plus q and minus q on a straight line at equal distance. So let's take the distance between them as r, and also they have said us that the potential energy of the system of these three charges is equal to 0. That means the total potential energy of the system, which is the sum of potential energy of any two charges, is equal to 0. That is, potential energy of minus q plus q plus the potential energy of q and minus q plus the potential energy of minus q and minus q, which comes out to be the total potential energy u, is equal to 0. So we can say 0 equal to potential energy of minus q and plus q will be 1 upon 4 pi epsilon naught minus q into q by the distance r, plus potential energy of q and minus q, that is 1 upon 4 pi epsilon naught q into minus q by r, plus the potential energy of minus q and minus q, that is 1 upon 4 pi epsilon naught q square upon, now this is separated by a distance 2r, so 2r. Now taking 1 upon 4 pi epsilon naught common, we get 0 equal to 1 upon 4 pi epsilon naught, this minus q and q minus q will get common, so 2 times q by r minus plus q square upon 2r. Now if we take 1 upon 4 pi epsilon that side, so we'll get 0 equal to minus 2q by r plus q square upon 2r. So if you move this on the left hand side, we'll get 2q capital Q upon r equal to q square upon 2r. R gets cancelled, q and 1q gets cancelled, so we get, if what we want is the ratio of capital Q to small q, so capital Q and this small q will come out to be, if this 2 gets here, it will be 1 ratio, so the ratio of the two charges is 1 by 4. I hope you understood this sum. Let's look at the next sum. A capacitor has some dielectric between its plates and the capacitor is connected to a DC source. The battery is now disconnected and then the dielectric is removed. State whether the capacitance, the energy stored in it, the electric field, charge stored and voltage will increase, decrease or remain same. So solution. So first of all, let's denote the capacitance of the capacitor when dielectric was there by CD, which is equal to K times epsilon naught A by D, and when the dielectric was removed, the capacitance will be C equal to epsilon naught A by D. From these two equation we can say that CD is K times C, which implies C will be CD times K. That is, when the dielectric is removed, the capacitance is decreased by a factor K. Now we know that the charge stored in a capacitor will remain same when dielectric is placed or when the dielectric is removed. That is, QD is equal to Q. So QD can be written as, now we know that Q is given by CV. So QD can be written as CD VD equal to CV. So VD will be CV by CD and C is given by CD by K. So CD by K into CD by V. So CD gets cancelled and we get V by K, which implies VD is V by K. That is, or we can say it, V equal to VD into K. So from here we can conclude that when the dielectric is removed, the potential will increase by a factor of K. Next thing, we can find out the energy stored in the capacitor when the dielectric is placed. That is, UD can be written as half QV QD VD, and the energy stored when the dielectric is removed can be given by U equal to half QV, which can be written as half Q and QD were same, so we can write this as QD, and V is VD times K, so VD times K. So this is equal to K times half QD VD, which implies U will be equal to this half QD VD is the energy stored in the capacitor when dielectric was there between the plates. So U is K times UD. That is, when the dielectric is removed, the energy stored is increased by a factor of K. Now the last thing we can find out is the electric field. Now we know electric field is given by E equal to V by D. So the electric field when dielectric was connected, ED can be written as VD by D, and the electric field when dielectric was removed can be written as V by D. Now V is VD by K, so V can be written as VD into K by D. So VD by D is electric field when dielectric was connected. So we get E equal to K times ED. That is, when dielectric is removed, the electric field is also increased by a factor of K. So these were the conclusion that we made. So I hope you understood this sum. Let's look at the next sum. Find the ratio of potential difference that must be applied across a parallel and a series combination of two capacitors C1 and C2 with their capacitance in the ratio 1:2, so that the energy stored in these two cases becomes the same. So solution, we have two capacitors C1 and C2. So C1 ratio C2 is 1 by 2, which implies C2 is 2 times C1. When the capacitors are connected in series, that is C1 C2, the equivalent capacitance Cs will be C1 into C2 by C1 plus C2, which can be written as C1, since C2 is 2C1, so 2C1 C1 plus 2C1, which can be written as 2 by 3 C1. And when the capacitors are connected in parallel, the equivalent capacitance, that is Cp, will be C1 plus C2, which can be written as C1 plus 2 C1, which is 3 C1. Now what they have said is that we need to find out what potential difference must be applied so that the energy stored in these two cases becomes same. So we want, when the capacitor was connected in series, the energy stored, and when the capacitor was connected in parallel, the energy stored must be equal. For that we need to find out the potential difference that must be applied. So you know that energy stored in capacitor is given by half CV square. So when the capacitors were connected in series, it will be half CS Vs square, which will be equal to half. Now when the capacitors was connected in parallel, Cp Vp square. So half gets cancelled, and we know value of Cs is 2 by 3 C1 into Vs square equal to Cp is 3 C1 into Vp square. So C1 also gets cancelled, and we get Vs square by Vp square equal to 9 by 2, which implies Vs by Vp will be 3 by root 2. So this is the ratio of potential difference that must be applied for the two capacitors for their, when they are connected in series and parallel, so that the energy stored remains the same. I hope you understood this sum. Let's look at the next sum. Two charges of magnitude minus 4q and plus 2q are located at a point 2a and phi a on the x-axis respectively. What is the electric flux due to these charges through a sphere of radius 4a with its center at the region? So let's draw x-axis and y-axis, and we have a sphere of radius 4a. So suppose this is 4a on the x-axis, so we have a radius of 4a, and the charges are placed on the x-axis at a distance of 2a and phi a. So one charge is placed at a distance of 2a and other charge at a distance of phi a. So at 2a minus 4q is placed, and at phi a plus 2q is placed, and we need to find out the flux due to these charges through a sphere. Now from the Gauss law we know that the total flux is given by charge enclosed by epsilon naught. Now in this sphere only one charge is enclosed, that is minus 4q, because the other charge plus q is outside the sphere. The total flux will be due to minus 4q charge, so this can be written as minus 4q by, so this is the total flux that will be coming out of the sphere of radius 4a. I hope you understood this sum. A capacitor of 6 microfarad is charged by a 300 volt supply. It is then disconnected from the supply and is connected to another uncharged 3 microfarad capacitor. How much electrostatic energy of the first capacitor is lost in the form of heat and electromagnetic radiation? So initially a capacitor of 6 microfarad is connected to a 300 volt power supply. So 300, and it is charged. So the energy stored in the capacitor will be, in this case, U1 equal to half CV square, which is equal to half, C is given as 6 microfarad, that is 6 into 10 raised to minus 6 farad, into V square, that is 300 square. Now solving this, you get U1 equal to 27 into 10 raised to minus 2 joules. Now in the second case what they have said is that this capacitor is disconnected from this voltage source and connected by another uncharged 3 microfarad capacitor of 3 microfarad. Now the total capacitance will be, since they both are connected in parallel, so total capacitance Cp will be 6 microfarad plus 3 microfarad, which is equal to 9 microfarad. And from the first condition we can say that the charge stored in the capacitor was Q equal to Cv, which is 6 into 10 raised to minus 6 into 300 volt. So Q we get as 18 into 10 raised to minus 4 coulomb. Now we know that the total charge in the capacitor will remain same. So in the second case, the energy can be given as U2 equal to half Q square by C. And since the charge remains same, we can say that half 18 into 10 raised to minus 4 square divided by the total capacitance, that is Cp, 9 into 10 raised to minus 6 farad. So we get U2 equal to 18 into 10 raised to minus 2 joules. Now this is the energy in the second case. Now we need to find out the energy that is lost. Now the energy lost can be given as U1 minus U2, which is 27 into 10 raised to minus 2 minus 18 into 10 raised to minus 2 joules. So we get energy lost as 9 into 10 raised to minus 2 joules. So this much energy is lost in the transition of removing the 300 volt supply and connecting another capacitor of 3 microfarad. So thank you for watching this video, and the remaining sums we'll do in the next part of this video.